Okay, so Unit 4 is the last of the stuff from that's like a year old or more. So that was the last of the stuff that I really wanted to make sure we review because like we learned it, but a long time ago. So that's what we're doing today. But a lot of this has been skills that we've just been using all the time anyway, like balancing an equation and stoichiometry. So we're going to breeze through some of this stuff, and I'm really going to focus in on the oxidation and reduction, which we haven't done in a while. And we'll try and hit that primarily. So, okay. No, don't do that. Yeah. Okay. So yeah, chemical, physical changes. Like I'm not even going to bother. Like signs of a chemical reaction. That's so Chem 1 stuff. You know that. The only thing I will kind of point out is don't forget that phase changes in the state of matter are physical changes. You are breaking forces, not bonds. So that is this first part is one thing that you do need to make sure you remember, although I don't think that that's actually an issue anymore. Yeah, like I'm not even going to bother going through these practice problems because that's like intro level Chem 1 stuff. Net ionic equations. All right, so this will practice a little bit. So don't forget, they can still ask you to write a net ionic equation on this test. So they have traditionally been moving towards providing you the full molecular equation on the top and then asking you to write that down into a net ionic. So remember that for us, what we were saying was the easiest thing to do would be to say, okay, so I scan across and I look at everything and I'm like, okay, let me look at these states of matter symbols and then be like, oh, solid. That's the thing that's going to stay. So this thing I know is going to stay completely intact, and I would just immediately write that and then work backwards and say, so my PB, and then you have to write it as the ion, and everything on the left-hand side is going to be aqueous for net ionic reactions always. And then the other thing you would write, the iodine, you would write with its charge, and then you have to remember any of the subscripts here are going to become coefficients on the left-hand side. So that's kind of how we started just going through a shortcut. They are never, ever going to ask you to write a complete ionic equation. That's often how it's taught that you get from one to the next, but you don't have to if you just identify the thing that doesn't split up like you did up here with the PBI2 and drop it down. So everybody remember that's how we're doing that?
Yes.
Cool. All right. So old school. Balance that thing. Figure out what coefficients go where. So how many coefficients would this have?
They all need to be changed.
I want to say 3. Oh,
3,
all of them?
yeah, all but
3.
one. All but one of them. This one, the aluminum sulfate, does not need a coefficient. So what are you putting in front of the aluminum hydroxide?
2.
2. And in front of the sulfuric acid?
3.
Yeah, the 3. And in front of the water?
3.
Yeah, that's the annoying one. It's 6.
Oh.
If you look at it here, that 3 H's there, right? But 2 times 3, so that gives you 6 H's. but then once you put this 3 here, that's another 6 H's. So you need 12. So that's why you got to put the 6 there to get that. So kind of annoying, but that's all right. The other way to think of that, remember, is this is one of those, since this is technically a neutralization reaction, you can look at this as HOH. And there you see the first H here is this H, so that's those connected. And then this is the OHs connected, and you can balance it that way. That works for neutralization reactions. Okay. All right, so write a balanced equation and a net ionic for potassium phosphate and aluminum nitrate. Now, again, they're not going to give you words without giving you the formulas anymore. So what is the formula for potassium phosphate? Let's do that really fast.
K3.
What's the charge on phosphate? You remember?
Just 1 plus 1.
All right, yeah, the potassium is 1.
Yeah. Oh, phosphate.
Phosphate is
2.
not 2. It's the one that's not 2.
3
3,
minus?
yeah. It's 3. So that's K3, PO4. And then aluminum is also a 3, and nitrate is a
2.
1.
Damn it. I hate trying to figure out charges because I always forget.
Yeah, well, it's not going to be an issue now because we're going to annotate the crap out of your periodic table as well as have the most common polyatomics written out for you. So,
Which means I'm going to pass this AP test, I think.
so, but again, anymore, they're going to provide those formulas for you, and then you have to finish it from here. So they would normally now say potassium phosphate in parentheses K3PO4 and aluminum nitrate in parentheses AlNO3, and they would ask you to do it from here. So now, what do those two produce and balance?
KNO3 and AlPO4.
Yup. So AlPO4 and KNO3, again, since it's 3 and 3 and 1 and 1, there's no additional subscripts there. So if you're looking at that, then for the net ionic is going to be based off of which compound?
AlPO4.
AlPO4 is what you will then drop down and then split it to make your reactants.
So Al3 plus PO4. 3 minus.
Yep. And they did clarify for us that they are not expecting people to write the AQs and stuff. So just know that you'll just have to make sure you have the charges in there correctly. That will be the focus. All right, so yeah, there's that. And then this one, again, sodium fluoride reacts with nitric acid. Write and balance the net ionic equation for this. So sodium fluoride, NaF, and then nitric acid. And again, we'll list out your acids and all that sort of stuff so you've got them. Acids always start with a what?
Hydrogen.
Hydrogen, right? Nitric comes from nitrate, so it's H.
Oh, shit. I'm on mute. Sorry.
That's okay.
I'm like, you didn't just hear me say H.
HNO3. So what's going to be what are the products here then?
HF and NaNO3.
Right. So HF And
Hydrogen fluoride?
yep, hydrogen fluoride and sodium nitrate. So which one of those, right? We don't have any information about solids or anything like that. Which one of those is going to make the solid or the thing to drop down into the net ionic?
NaNO3. Is it NaNO3?
It is not. It is the HF. Because what never makes solids?
Oh,
Na. What's
Na
that? Sodium.
and NO3s. Neither of those are ever going to make solids. So you're always going to drop those out. So just like up here, right? The the nitrate up here is never going to do anything, and potassium also, right? Alkali metals never ever going to do anything. So that's how you know it's those. Solubility rules. Okay. All right, we know they're not going to test this skill this year because they've said specifically that you don't have to draw any diagrams. So then you just got to remember that the rule for particle diagrams, since you're not going to have to draw one, is just to count the things. So we already know that. You're just going to count the things. If they give us a picture, we're counting all of the things. Moving on. Physical chemical changes, like, come on. We're not even bothering. We know all that. Yep. Stoichiometry. We know how to stoichiometry. We know how to do that. But let's review a few little things. So if that's my equation, how do I go about setting this problem up? We don't actually have to do all the math. We can just talk it through to make sure everybody knows where to start. So if you were looking at your mole map, where are you starting?
Molarity?
Moles, no, with moles of sulfuric acid.
I'm starting with volume of solution.
Oh.
And then you use the molarity to get to moles of sulfuric acid.
Okay.
Okay, so I've got this much, and I'm starting with this thing. And then what is it asking me to find?
Moles.
Moles of copper.
The moles of copper, and I think they meant sulfate, not carbonate.
Yeah.
Or no, phosphate, not. All right, but still, that's clearly phosphate. So it's asking for that. So it's really just a two-step problem. All right, so, and here you can do, the cheater way to do it is to say 30 milliliters times 1.5 moles over 1,000 milliliters instead of 1 liter. So it's basically incorporating that conversion into the setup. So that works in this regard. So I could do that. That's my first step. And then the second step is simply the mole ratio. So 3 of the sulfuric acid to 1 of the copper phosphate on top. So that's all that one is. That's the answer you would get, but we're not going to worry about it. What is the percentage yield of hydrochloric acid if 11 grams of calcium chloride produces 6.6 grams of hydrochloric acid? So percent yield, this is a lab thing. So this is fair game. So we need to remember what percent yield is. It was a basic formula. Remember, every percentage is simply a part over a whole. So in this instance, part is the actual All right, otherwise known as the lab amount, right? This is what you get in the lab and over the theoretical. And the theoretical is what you would calculate. So the other way to look at this is lab over calculated. So they have to give you the lab amount, the actual amount. So what is that? Which of those two numbers is going to go in the numerator?
The 6.6 grams.
The 6.6 is my lab amount. And the problem is set up as such where you have to take this other amount and you have to calculate it. So I've got this and I need to go to this. So it's just setting up a mass problem. Calcium chloride, so converting the grams of calcium chloride to moles of calcium chloride, converting moles of calcium chloride to moles of hydrogen chloride, and then moles of hydrogen chloride to mass, and then it would go from there. So I think the only thing needing reviewing there is what this actual formula is. And we'll make sure to put that on your formula sheet when we annotate it next week. And I'm gonna send out a clean copy so that you can, if you can print, you can print out a clean one. Okay. And if you did that problem, 91% would be your answer. The last one, take the reaction. In an experiment, 3.25 grams of ammonia are allowed to react with 3.50 grams of oxygen. What is the maximum mass of NO that could be produced? So you should be able to recognize that. How many givens do you have in this problem?
2.
You have 2. There's this one, and then I have this one. 2 different things, right? This guy and this guy. You remember what it's called when you have 2 different givens, 2 different reactants? Starts with an L.
What's the next letter?
I.
What's the next letter?
M.
Lime.
Shut up. Limiting reactant.
Limit. Ha
Yeah.
ha ha. I said it first.
Okay. So this is a limiting reactant problem. And all you're going to have to do for a limiting reactant problem is it is 2 mass problems. So you'll set up 2 mass problems, all right? And then once you do that, how do you know which answer is the correct answer?
Whichever one puts out the least product.
Yes. Yes, you'll set up 2 mass problems and then pick the smallest number. That is correct. So pick your smallest. Okay. All right, so that's how you would do a limiting reactant problem. That is also a lab type scenario, so it's certainly possible that that is a very fair game question. So when we go over lab techniques next week, we'll mark up that this is basically something. This is one possible way that you would actually have to do stoichiometry. These 2 last questions kind of go together, right? The limiting reactant problem, figure out how much should you make. Oh, here's how much you actually made in the lab. Now calculate the percent yield. So that's one way that they could get this skill in. It would easily incorporate into a lab. And we do know that that is where they are focusing their energy on these questions as more lab scenarios. Okay. This is another limiting sort of problem. So this was actually designed to be a multiple choice question because the numbers that they gave you are very, very easy. So the question is asking for moles of carbon dioxide. So that's this guy. So I have 64 grams of methanol. So I need to do one problem figuring out that. And then the other one is the 44.8 liters of oxygen. So I need to do another problem doing that. But you should easily be able to tell how many moles of methanol do you have. They nicely gave you the molar mass.
2.
So 2, right? So if I have 2 moles of methanol, how many moles of carbon dioxide am I going to make?
2.
2. So that one's going to give me 2 because it's the stoichiometric ratio. If I look at the oxygen, how many moles of oxygen do I have if it's 44.8 liters?
No, so 2.
Also 2. Because remember, the magic number with STP is 24, or is 22.4. That should be on the formula sheet. If not, we'll put it on. So 22.4 liters of gas. So that's 2 moles. So I have 2 moles of this. If I only have 2 moles of that, how much of carbon dioxide am I going to make?
Less than 2 moles.
Less than 2 moles.
Yes.
4/3, 1 1/3, 1.33, right? Something like that. So yeah, so this is an old multiple choice question, and that's why I was like, you know, yes, you would have to do math on the multiple choice, but it was set up with numbers like this, so where it shouldn't be that hard. But okay, so that's stoichiometry. Titration. All right, titration is a lab technique, and this is the lab technique we did this year, the beginning of the year. So let's see what you remember, and we will review this again when we specifically review lab techniques next week. But the titrant is what you know, the known concentration. Do you remember what piece of equipment you put the known solution in? It's all right. We'll see if there's when the picture comes up, if it triggers your memory. The analyte is what we don't know, is the unknown. So you always have the known and the unknown. And then to do titration, we use a burette. So which of those two things goes in the burette? The thing you know or the thing you don't know?
The titrant.
The titrant, the thing you know. All right, so the titrant is always going to go into the burette. And the analyte is going to be in a flask or a beaker or something like that. We tend to use a flask because it's easier to make it swirl. Okay. And then that's the lab setup. Does that seem familiar? You remember when we did that?
Yeah.
Yeah. Okay. So, okay. So there's multiple ways you can do a titration. Okay. Let's see here. The main way we did titration was with acids and bases. And we used an indicator to change color. And the most common indicator that we used was the phenolphthalein. And remember, we were trying to get the prettiest of the pale, pretty pink. So that's kind of nice. All right, so we slowly drip stuff in from the burette. This is an annoying thing that they might actually ask about. In theory, you should rinse out your burette with the stuff you're using for a couple of times. Now, they don't say why you should do that, but the reason you should do that is to make sure that you rinse out any water, because water would dilute your concentration. Remember, the stuff in the burette is supposed to be the thing you know. The concentration of the stuff in the burette is supposed to be exact. So if there is any water left over in the burette, it will dilute your sample, and that will mess up your calculations. So I don't think they'd ask about that, but just in case. All right, and then yep, we put stuff in a flask. Indicator, you can't forget the indicator. If you forget the indicator, you have no idea when to stop. And then you keep going until you reach the end point. And for us, the end point is when it changes color. Or if you're monitoring it with a pH meter or something like that, it's when it would reach the desired amount. But for the most part, we do these things when they actually change color. And then you just do straight stoichiometry, right? So this would be volume and molarity and a mole ratio and a volume, and you're calculating a final molarity is typically how that ends up working out. So this is kind of a grainy picture, but I can tell you in the last 4 years of AP chemistry tests, they have had a picture exactly like this in 2 of the 4 years. So clearly they want to be able to assess that you can read a burette. So before we even look at the question, I know it's a little hard to read. What volume would you say, what reading would be on this first burette on the left? What does that look like?
5.5.
5.7.
Well, 5.5 would be at that line. So
5.4.
7.
it's not technically all the way down to 7, because 7 would be at that one.
5.65.
5.65 is what they're looking to have you read. So on a burette, you can estimate to this place. That is the expectation, is that you would estimate to that place. So then what is the volume on this one on the right? That's a 37, in case you were wondering.
37.3.
37.3. So technically it would be 37.30. So then the question would be, how much stuff was drained out? How much was used?
$31.65.
31.65.
What's the plus or minus 0.5 milliliters?
So I think they meant plus or minus 0.05 milliliters, because this was a question where they were asking for correct sig figs. And so the sig fig is actually in this last decimal spot. So that should be 0.05. But that's what that is. So it would be kind of crazy that they would do this, because they did have a burette reading on last year's test. So it does kind of seem to be every other. So maybe you won't have a burette question. But one of the reasons that we did so much stuff with burettes this year was so that you would get comfortable reading them, because I know that that's a skill that they ask a lot. Okay. So then it says, if the concentration of that sodium hydroxide is 0.1, how many moles of hydroxide were added? So what do you need to do for that calculation?
Are you going from I don't know, actually.
Oh, I see.
So 31.65 would be
Yeah. Nope.
0.03165
Mhm.
liters.
Oops.
And then you simply multiply that by the molarity, 0.10. And that would give you the moles. So that's just moving your decimal over one additional spot. So 0.03165. Yeah. So that's that. So that's the titration stuff. Types of chemical reactions, I mean, they've never actually asked specific questions about like, identify what type of reaction this is. It's more like we recognize that there's acid-base stuff, precipitation, right, forming a solid, so they'll ask you some sort of net ionic, or oxidation reduction, where they're going to ask you something about oxidation numbers. So, right, acid bases in general, right, you've got an acid plus a base making water and a salt. That's our basic acid-base reaction. Oxidation reduction, this is when you have a transfer of electrons. This was a while ago. This is what we will, we're going to review, is what is oxidized and what is reduced. And then precipitation is when you have to follow your solubility rules and you have to figure out what makes the solid. All right. So oxidation numbers, in the way, way back machine, probably in January of last year. So over a year ago is when we've done this. So when you are looking, you have to remember elements in their elemental form have an oxidation number of 0, meaning iron solid is a 0. O2 gas is a 0. Anything by itself as a normal element is a 0. Things that are telling you their charge, because they are telling you their charge as an ion, the ion tells you the oxidation number. It's the same thing. So the oxidation number of Fe2 plus is +2. The oxidation number of F -1 is -1. So if they tell you the charge, that is the oxidation number. So that's lovely. And then we start having things like, we typically always assign oxygen as a -2. We typically always assign hydrogen as a +1 because hydrogen is almost always bonded to other nonmetals. Fluorine is always a -1. And most other things we're gonna have to figure out. So I figured this might be the thing we need to actually review how to do. So let me actually switch over to my iPad really fast. Come on. There we go. Okay, so if you had something like, oops, so KClO3. So let's assign oxidation numbers to everything that we know to begin with. So who in that list do we automatically know one of?
Oxygen.
Oxygen. Oxygen is going to be a -2 because it essentially always is. And then there's one other thing that we can automatically assign.
Oh, is it potassium?
It's the potassium. And that list of rules didn't say it explicitly, but your metals, your regular metals have their regular thing. So what is potassium's regular charge?
+1.
+1. So that's its oxidation number. So then what we have to figure out is what chlorine is. So do you remember I was like, okay, so I've got 3 of these -2s, which is a total of -6, and I've got a +1. So what does this have to be for all of that to equal 0?
+5.
+5. And that's how we did that. Does that seem familiar?
Yes.
Yeah.
Okay. So it's not too hard. It's just we haven't done it in a minute. Okay. So solubility rules, those were a little easier because we know who is never making a solid. Which things are never going to form a solid?
Na,
NaNO3.
NO3.
Na, NO3, K, yep. Ammonium is the other one, right? I mean, and really, these are any of your alkali metals, right? But the most common ones we end up seeing are sodium and potassium. I suppose they could throw in a rubidium or a lithium, but for the most part, sodium and potassium. So your alkali metals, never going to make solids, your ammonium and your nitrate. So those are the things that we're looking for there. That makes that easier. Blah, blah. Yeah, that's easy enough, whatever. Okay, so let's figure out this one. In this reaction, which element is being oxidized and which element is being reduced? So first, to be able to do that, we have to assign oxidation numbers to everything. Except it's not actually that hard to figure out because 2 of my elements in there don't change at all. Which 2 elements are not changing in there and are the same across the board?
Wait, what's the question?
We get to assume the oxidation number of 2 of the elements listed there. Which ones do we get to assume?
Oxygen and hydrogen.
Yeah, we get to assume the oxygen and the hydrogen. So I know it's not those. So that means I'm going to focus on the manganese and I'm going to focus on the chlorine. And essentially, I can look at this and say, okay, so one of those is oxidizing and one of those is reducing. So I just need to figure out what their oxidation numbers are and figure it out from there. So this chlorine is easy right here. So the chlorine on the left, it's an ion, which means its oxidation number is its charge.
-1.
So it's got to be -1. But if I look over here and I see that this whole thing is ClO3 with a minus charge, and I know the oxygen is a -2, and there's 3 of them, and I have to have 1 left over, what is this chlorine on the right?
5.
It is a +5.
So it's oxidizing.
Okay. And then just for practice, we'll switch over. The manganese right next to it. So I've got 2 oxygens at a -2 each, but there's no charge here. So I've got 2 -2s. So this manganese on the right has to be a what?
+2.
No, it's not a +2.
Wait.
I've got 2 of the oxygens. Yeah, 4, +4. But on the left over here, I've got...
Wait, so what does the subscript, what does the subscript do to, it doesn't do anything?
The subscript does, the coefficient doesn't matter.
Yeah, the
Yeah.
coefficient.
Yeah,
doesn't do
coefficients
anything.
don't matter when you're figuring out the oxidation numbers.
Okay.
Yeah, so I can ignore them. So the only thing you have to pay attention to is like that there is a minus sign right here, right? So I've got 4 oxygens that are -2 each, but I'm supposed to have 1 minus left over, which means this manganese on the left is a plus what?
+7.
7. Okay, so you can assign the oxidation numbers. Now you got to remember between oxidized and reduced what those terms mean. And I said that if you remember that reduced means that your number actually went down, your oxidation number actually went down, and that oxidized means that your oxidation number went up. So whose oxidation number went up, left to right?
The chlorine.
The chlorine, and therefore by default the manganese went from 7 down to 4, so the manganese was reduced. So little crash course right there. Yeah. So okay, identifying oxidation numbers there. 2 of those are super easy.
H and O.
H and O. So I know the O is a -2 and the H is a +1. But then I got to figure out the other things. So it's actually easiest if you break this up and say, okay, I've got the polyatomic ion, SO4. That whole thing has a 2- charge. And I know that my oxygen is a -2, which gives me a total of -8, but I'm supposed to have 2 left over. So my sulfur must be a +6. And then if I do the same thing with the ammonium, I know that this is NH4 with a +1 here, but I know that the hydrogen is the positive one here, right? This is the +1, and there's 4 of them. So what does the nitrogen have to be?
6.
No? That's going to give me a total of +4. I'm supposed to have a +1 left over.
-3.
Okay, now I'm confused because of the charges of the things. Because, like, what is it? Okay, so you're saying you're supposed to have 1. Okay, can we start with the SO4?
Mm-hmm.
Well, we have 2 left over.
Yes.
What does that mean? I'm adding 2 or, like, subtracting 2 from?
So it means that when you are looking at these 2 numbers, between this +6 and this -8, I'm supposed to be left over with 2 negatives.
Oh.
That's what it's telling me, is that I have to have more of my negative in the oxidation than I do in the positive.
Okay.
So this is telling me that I need to have, out of all of these, I have to have 1 of them left over. So therefore I can only cancel out 3 of these +4s because I'm supposed to have 1 left over.
Okay.
Okay. All right, and there we are. We did that right. Okay, who cares about that? That's fine. Okay, same thing. Okay, so a word about this topic. This introduction to acid-base reactions, we did not actually cover this topic because we were going to cover it in acids and bases. And nobody thinks they're actually going to ask anything about these acid-base definitions because there's nothing they could do with it if you don't then have the entire acid-base unit. So we're not going to worry about this topic because it's not really going to be applicable because there's nothing to do with acids and bases since they chopped out that entire unit. And then going back again to oxidation reduction, we already went over element oxidized, gaining, losing, oil rig. And the other thing I said was Leo goes ger is the other mnemonic there. But as long as, I mean, you guys immediately remember that the oxidation numbers go up or down. And yeah, we've practiced this. We've practiced it. We're good. We're good. So that means we are done with, we are done with Unit 4. Because it was mostly stuff from last year, and I really just wanted to mostly go over hitting the limiting reactant stuff, the oxidation reduction, and the titration. So there you go. I think, as I said, every single personal progress check is open. The things that are grades, the Unit 3 and the Unit 4. So you've got a set of collaborative notes and the personal progress checks for Unit 3 and Unit 4. Those are your actual graded items. And again, they're completion grades. So just do them. Then Units 5, 6, and 7 are open. Those are all the things we did this year. So kinetics, thermo, and equilibrium. That's those 3 units. So those personal progress checks are open. If you just want to play around with the free response questions on those, because that's what our test format is, that's fine. On Monday, we are going to do practice free response questions from Unit 4. So I'll have a titration question, I'll have a limiting reactant question, and I'll have a question that lets us practice oxidation and reduction. And these are all going to be lab-based questions because Unit 4 definitely ties into lab-based stuff. And then next week, so that's Monday. Wednesday, we're going to spend the day talking about the test and annotating our periodic tables and formula sheets. And Friday, we're going to review lab techniques. And that's what next week is. So there you go. Anybody have any questions? Because otherwise, sayonara and goodbye.
Sayonara.
And goodbye.
And goodbye.
Mhm.